that's fine.
Okay, well, we're very happy to have for our last seminar of the quarter, Hofie Hannesdottir. Is that reasonable facsimile of the pronunciation, I hope? Anyway, I think you got your PhD at Harvard, and this was your first postdoc, is that right? First
That's right.
postdoc at IAS. Has done a lot of nice work on scattering amplitude, and she's going to tell us about what can be measured asymptotically.
Yeah, thanks a lot. And thanks a lot for the invitation. I'm very happy to present this work, What Can Be Measured Asymptotically, which came out last fall in a couple of papers in collaboration with Simon Cronho, Mathieu Giroux, and Sebastian Meisera. So let me start with the motivation. So we all know of two observables that can be measured asymptotically, namely the amplitude and the cross-section. And they are even connected, as we know, by unitarity in this simple way. So the imaginary part of the forward amplitude, let's say for PP to PP, is proportional to the total cross-section. So what we want to ask in this talk is, first of all, are there more observables we can measure at infinity? And if so, how are they related to one another? So let me elaborate on that. The questions that we're going to ask is, first, what is the class of asymptotic observables that can be measured using only data at infinite times? And second, what is their physical interpretation and what are their IR divergences? And third, how are asymptotic observables related to each other? And what we will find at the end of the talk is that we will have found a host of asymptotic observables, and they will have different physical and analyticity properties, and they'll also have different time delays or IR divergences. So here I've given you just a preview of something that we're going to find, and we're going to start drawing diagrams like this. So this denotes the S matrix. And this is a different observable than the S matrix. It's almost S stagger stitched together, but there is actually an extra particle emitted here. And we're going to see that these two correspond to observables that we can measure with only data at infinity, but they're going to have these. And in particular, for example, these two are going to have different infrared divergences. So one important point is that the boundary data is not sufficient to label the observables. We'll see that in addition to the boundary data, we also need to specify basically the time contour. So here's an outline of what I'm going to talk about. We'll start with almost the title, what can be measured asymptotically. So we'll classify all these different asymptotic observables. Then we'll talk about how to use a new form of LZ type reduction formulas to compute them. In part 3, we'll talk about their physical properties and infrared divergences. And then in the fourth and last part, we'll show how to connect these observables to each other via new versions of crossing symmetry. So what that means is that we'll show how these different asymptotic observables are connected by analytic continuations in the complex plane. And let me emphasize that this last point was really a huge surprise, at least to me, and something very unexpected that came out of this story. So let me actually pause here if there are any questions before we go on about the motivation. If not, let's just start. So the first thing that we're going to talk about is the asymptotic algebra in quantum field theory. And before we do that, let me emphasize that we can use this asymptotic algebra whenever the S matrix makes sense. And that's when we're going to write down axioms for this asymptotic algebra. So for example, this could be something like pion scattering in 4 dimensions, which is perfectly infrared finite, but it's also fine to use this construction, for example, in perturbative QED or QCD, as long as we use dimensional regularization or any other regulator for the divergences that we have. So that was just a point that I wanted to emphasize, that a lot of what we're going to talk about is going to be non-perturbative, but it's absolutely fine to expand in perturbation theory as well. And despite having infrared divergences, for example. So here is the algebra. A lot of this might be familiar from quantum field theory textbooks. So we assume that we have an algebra of asymptotic measurements in the far past and far future. So we have creation and annihilation operators that satisfy these commutation relations. And you might see these written as A in and A out in textbooks. But here we use the notation A and B. And the reason for that is that we're going to start writing many of these in sequences, and it just gets too cluttered if we have superscripts and subscripts and daggers all over the place. So just remember that A are the past operators and B are the future operators. So these satisfy the traditional commutation relations. We also assume that these operators act on equivalent Hilbert spaces and that they're related by a unitary evolution operator that we call S. So basically the future operators are obtained from the past operators by evolution with S. And this is all in the Heisenberg picture. So we have B equals S dagger AS, and same for B dagger. And then we also use, we assume unitarity. So we assume that SS dagger is 1. We also assume that there exists a time invariant vacuum that we call 0. So the vacuum is annihilated by all the annihilation operators, as usual. And the vacuum evolves trivially with the S matrix. The last point might be the one that's maybe least familiar. That's the point of stability. So basically what this last point is telling us is that if we have a one particle state that we call A dagger acting on the vacuum, and we evolve that one particle state with the S matrix, then basically nothing can happen to it. So what that says is that if we have just one particle going along, it can't evolve into anything. It has to stay that particle until it interacts with a different particle. So that's why we call this condition stability, and it holds for both the past and the future operators. Let me also give a few caveats that we assume Bose-Fermi statistics, flat space, and Poincare invariance. We could start discussing what happens if we relax one of these, but actually all of them were important for some of the things that I'm going to talk about here. So using this algebra, what can be measured asymptotically? So let's start at 4 points. Assume that we have 4 particles in our process. So here we can string together 2 A operators and 2 B operators. Actually, because of stability, we always have to have basically 2 A's or 2 B's adjacent to the vacuum. So one thing we can get is this B4, B3, A2 dagger, A1 dagger. And now we use our axioms that B evolves with the S matrix. And using unitarity on this side, we actually get that this is precisely equal to the S matrix for 1, 2 going to 3 and 4. So this might look familiar. We have some past operators that create 1 and 2, and then we have some future operators which annihilate 3 and 4, and that's precisely the S matrix. We can also have the daggered version of this, where we have 2 B's followed by 2 A's. And then we can also have a string of A's or a string of B's. But actually, these are forward terms. So they only have basically support where, let's say, 1 and 3 are exactly the same particle with the same momenta, but we're going to assume that we're not in that configuration. So we're going to set all these forward terms to 0. One thing that we're going to do in this talk that is not a traditional convention is that we're going to have time flowing to the left in all of our diagrams. The reason for that is because we've kept the traditional operator ordering, but since we're going to start drawing strings of these, it got very confusing if we're always reversing the pictures with regard to the operator ordering. So we had to pick one or the other, and we decided that the diagrams would have the time flowing in the opposite direction to what's traditional. Okay, this is actually all we can have at 4 points, but what about at 5 points? At 5 points, we can again write down the S matrix for 1, 2, 2, 3, 4, 5, and the S dagger matrix for 1, 2, 2, 3, 4, 5. That's fine. But now we can start having these new things. So for example, we can write down A1 dagger, A2 dagger, and then a B operator, a future operator, followed by two past annihilation operators acting on the vacuum on the left. So if we try to draw this using again our relations that B is S stagger AS, and we insert a complete set of states and have this what becomes an A3 act on that complete set of states, the diagrammatics would be like this. So it's particle 1, 2, going to 3, and then any particles in the set X that are allowed. And then we have the S stagger matrix for X going to 4, 5. So what I mean by this X here is that we insert a complete set of states and integrate inclusively over the phase space. And note in particular that this is not squared, and we cannot collapse this SS dagger by unitarity, because there is an extra operator here that prevents us from doing that. Basically, it's this operator in between this S and S dagger. So this is really something new. It's not 1, it's not 0, and we'll see its physical interpretation in just a moment. And then we can also do the daggered version of that and the forward terms and Hermitian conjugates. So to summarize, all measurements that we can have at 5 points using our algebra is the S matrix, S dagger, and then these new types of observables where we, for example, measure one future operator in the background of the past operators. And then we have the 3-to-2 versions of the same thing. So of course, the possibilities just grow. So at 6 points, we can have even more new things. So here we can have, of course, always scattering amplitudes where we stitch together A daggers and B. Now we can have something like inclusive cross sections where we have something squared. So these operators that are where we have in the future here are now quadratic and not linear. Or we can have out-of-time order correlators, which are basically maximal scramblings of these A's and B's. At endpoints, we can start enumerating all the different possibilities that we can have. So we can start stringing together basically any combination of A daggers followed by an S matrix, then A daggers. And we can have different countings of all of these. And we can actually do the count, and the number of distinct measurement types at endpoints satisfies this recursion relation here, which gives that it actually grows exponentially with the number of points, which is maybe not surprising. It's basically, we can scramble things in multiple different ways. But this shows us that scattering amplitudes, which grow linearly with n, actually form a very small subset of asymptotic observables as we go to higher and higher points. Okay, but now I've told you all of this, basically following from our axioms, following from our math, what we can have. But what's the physical interpretation? Again, we all know scattering amplitudes, and we can have those at any points. But as I told you, at 5 points, we can now have this new type of observable, which is basically measuring a linear operator in the future, which we call B3, in the background of some past operators 1, 2, 4, and 5. And it turns out that this object is precisely the ingredient that we need to measure the expectation value of an electromagnetic field in a scattering experiment. And it's also the ingredient we need to compute the gravitational waveform in the background of black hole scattering, as could be detected by a gravitational wave detector like LIGO, Virgo, and Kagra. We can also have some quadratic operators, and as we talked about earlier, these would be, for example, inclusive cross-sections or inclusive particle numbers, or these out-of-time order correlators, which are again these maximal scramblings of A's and B's. And I've included some references down here to some papers that actually have already been computing these observables in the past.
Sorry, can I ask a question?
Yeah, of course.
About the interpretation, because my understanding of when one uses, when you're interested in computing some expectation value of this, you would usually be using the in formalism. And in that case, the 5-4 would be equal to the 2-1. Would you agree with that, or are you thinking of something else?
Excellent, excellent question. We'll get to this a little bit later because we're precisely going to use the in-in formalism. The generalized LSZ is going to precisely incorporate the in-in formalism to compute these. And what we do to actually get the classical gravitational waveform, and that's why I said maybe a bit elusively that this was an ingredient in that, is that we take this part here, and then we basically integrate it against wave packets that are sharply peaked around the classical momenta of 1, 2, and 4, and 5.
Yeah, okay.
So it actually turns out that you need the off-diagonal elements. You can't set them exactly equal because this particle always steals a little bit of energy from the other two. So it's actually this kind of tiny off-diagonal part where you have a sharply peaked wave packet around the classical value. That is the final outcome as we actually compute the waveform. There's another question, I think.
Yes. So you said something about like gravitational wave detection and finding the like E&M fields they came from. But I thought you said that we assume flat space when doing these axioms. Do we have to modify that if something came from like a very gravitationally not flat space, like a black hole?
Yeah, excellent question as well. Here we do not have to do that, and we're relying on the techniques from the paper of Kosover, maybe, and O'Connell. Let me also be a bit more clear than what I had said. I was going to say this later, but since you asked, let me say this now, that actually this gravitational waveform from the scattering observables has not yet been detected, although there is hope that they might be detected in the future, because what it means is that the gravitational wave that's being emitted is actually from black holes scattering off each other, and not from black holes merging, which is what we have measured so far. So actually, it's fine in this case to work in basically a leading approximation where we assume flat space in this case.
Okay, so we have the black holes existing on a flat space background.
Exactly.
Black holes are our particles, not particles in a black hole background.
Exactly, and the black holes are just modeled as heavy scalars in this framework.
Got it. That makes sense. Thank you.
Thanks a lot for the question. Okay, so this is the last slide on this part. The takeaway points in this case are that scattering amplitudes are only one of exponentially many asymptotic observables, and that asymptotic observables are physical and they're already being computed and could be measured as well. And in this talk, as we mentioned a little bit, we'll talk about efficient computations and physical properties of scattering amplitudes and observables, and then we'll relate asymptotic observables to one another via analytic continuations. So let me bring the outline slide back. So now we've talked about what are the different asymptotic observables that we can build from our axioms. And now we're going to start talking about LSZ type reduction formulas, which provide an efficient way of computing them. So unless there are more questions, which I wanted to stop for.
So when you have higher point stuff, is the observable still going to be categorized just by these three amplitude EMN field emitted from scattering and the all-time order correlator? Like they always fall into these three category?
Not at all. Yeah, excellent question. Not at all. I mean, some of them we know exactly how to interpret physically. At some point, if we start stringing, so we can go back to this slide here. If we start stringing together many of these S's and S staggers, it's not clear in the general case to me what it corresponds to physically. So that's it's still an open question whether it has some physical interpretation in some cases. So for many of them, we do have a physical interpretation, but for also many of them, we don't, if that makes sense.
So I would like to make a remark. Are you hearing me?
Yeah.
Yeah. So I have written several papers about inclusive scattering matrix.
Mm-hmm.
And these papers really probably are very similar to the stuff that you're discussing. In
Excellent.
particular, LSZ type reduction formulas are proven in these papers.
Fantastic.
So it seems that there are other relations also, but let me say maybe a little bit more after your talk.
Excellent. Yeah, I would love to hear more about it. Thank you. Thank you for that comment.
Yep, please go ahead.
Great. Yeah, so let's now talk about the different ways that we can actually compute these asymptotic observables. So we actually are going to present 3 ways. So the first is a sum of amplitudes and cut amplitudes. Way 2 is using generalized LSZ formula. And method 3 is using analytic continuation. So this should actually be part 4 of the outline. It's the last part of the talk. And points 2 and 3 are really the one that highlight the physics. The first part is more kind of a trick that we can use, as we'll see. So let's go quickly over the first way, sums of amplitudes and cuts. So basically we can break the S matrix up into basically all different ways that we have a connected part and a disconnected part. So I've drawn some of them here, and we'll also need all different permutations. And in non-forward kinematics, what I said that we were assuming in the beginning, disconnected diagrams do not have support. So for example, if we write down this observable here, then we would not include a diagram like this one, where 3 and 4 basically don't interact with anything at all. So 3 just turns into 4, because this would be an overall disconnected diagram. But we do have to include partially disconnected, what's disconnected after the cut, basically. So even though for scattering amplitudes, we usually focus on the connected part, then once we have these more generalized observables, we'll actually need to take into account these partially forward diagrams as well. So now we can basically break down the S matrix into the disconnected parts plus the connected parts. So every asymptotic observable becomes a sum of just S matrices and conjugated S matrices with familiar LSZ and Feynman rules. So here I've written this out again for this gravitational wave expectation value. So this is supposed to be the expectation value of the gravitational field in the background of this black hole scattering. So we can write this if basically, if we take this S staggered to be 1, then there is a part of this diagram implicit that's just the usual amplitude for black holes going to a graviton plus 2 black holes. But there's also a different term, basically from taking both of these to be connected, which is like a Minkowski cut or a unitarity cut almost, which is black hole going to graviton plus anything, and then that anything going to, via the conjugated matrix, to 2 black holes. And recall that by X here, we mean a complete set of states that we integrate inclusively over phase space. So we can now use this method, for example, to compute the one-loop contributions to the gravitational waveform in the iconal approximation. And I've included one of the diagrams that we need to include in this computation, and it's a pentagon diagram, basically. So these are the 2 black holes, and then they can exchange gravitons. And I've shown here a few different ways, a few different diagrams that are included or not included. So for example, we always have to emit the graviton before the orange cut. So all of these are not included in this notation here because it's not matching the blob's pattern. Same here, we always have to cut through the entire diagram. So these 2 ones here, where we cut just some of the lines, but we don't cut all the way through, they would not be included because they're not unitarity cuts. Then there are a bunch of diagrams that are included, but they just vanish for kinematic reasons. But then we have actually non-trivial diagrams that are these 5 here for this topology. And note that these are really just the usual S matrices for these different pentagons and cross topologies. But then we also have a diagram here, which is genuinely a unitarity cut, where the graviton is emitted before the cut. So if we add these 4 diagrams, we would get the scattering amplitude. But if we include the cut term as well, we get this expectation value, this inclusive observable. Let me not stop too long at this method because we want to get to the generalized LSZ. So remember that the physical setup is that we measure the field of a graviton in the background of black hole scattering. So you can think of time as flowing basically forward to the left here, and then forward to the right on the other side of the cut. And the graviton is measured in the far future, and everything else is in the far past. And the reason why this explains a gravitational wave experiment is because the situation that we have when we measure a graviton on Earth, if we have our LIGO detector and we measure some displacement due to the gravitational field, we're not measuring everything else that's going on in the universe. So it's very different from a scattering amplitude where we really try to, let's say at CERN, we really tried to measure everything, all the outgoing states in our process. But here we're really just measuring one corner of phase space. There is a black hole scattering somewhere far away, and we measure the impact on Earth only. We don't have a spherical detector surrounding the whole universe. So the things that we fix are the graviton in the far future, but everything else is in the far past. So it's almost like a square of the process, but since we measure the field that's linear in the creation annihilation operator, it really corresponds to this diagram here. So we can work out, and we have this in our paper, that using nonlinear response theory, that this observable is represented by the retarded function, basically where we put the graviton in the far future of all the other observables. And I've included here the definition of the retarded function. It's basically the commutators of the field placing one particle in the future or the past of everything else. So the different time orderings can actually be put on a Schwinger-Keldysh contour. So we can imagine that once we have these different time orderings of the operators, we can represent those by time folds going backward and forward in time, but they're connected by this tiny imaginary part. So the time ordering and the retarded functions are both bases for different operator orderings. So we now want to derive an LSZ-like reduction formula that takes into account basically any kind of time ordering or retarded functions, etc. So we start very much in the traditional way, that the creation and annihilation operators are defined as surface terms of currents. So we have some current J of x that's given by this derivative in x squared plus m squared of phi. And if we write the current in momentum space and we take the on-shell limit, p squared going to minus m squared, then we can write this as a surface term. So we basically define the creation annihilation operators as this limit, basically picking out the surface terms of this integral here. And this becomes A dagger minus B dagger. So B dagger is the term in the far future, remember, and A is the term in the far past. And similarly, we divide these into incoming and outgoing. So everything here is so far just like in textbooks, but it's actually important for us to keep both of these terms, to keep the terms in the past and the future. So the scattering amplitude can actually be defined either as a time-ordered or a retarded product. So if we define it as a time-ordered product, we might, for example, define it as a time-ordered product of currents like this. P4 and P3 are outgoing, and P1 and P2 are incoming. And if we plug into our formulas from the previous slide, we basically get the time ordering operator of the differences B4 minus A4 for the outgoing particles, and A dagger minus B dagger for the incoming particles. And what the time ordering product now does is that it shoves all the B's to the left of all the A's. So actually the only term that survives when we expand out this full time ordered product is this B3, B4, A1 dagger, A2 dagger. So actually, and what you might see sometimes is that if we only care about scattering amplitudes, we can actually forget about this A4 and A3 from the beginning, and similarly this B2 dagger and B1 dagger, because in the time order product, they'll always be shoved to the side where they annihilate the vacuum. But in our case, it's actually going to be extremely important to keep this difference here, to keep the past and the future operators. So now we can also define the scattering amplitude as this, as basically the retarded product, where 3 is in the future of 2, basically sandwiched between these one particle states. Here we have a one particle state of 1, and here we have a one particle state of 4. And now we get the commutator of these operators. And again, this is the only term that actually survives. So both of these are perfectly valid representations of the scattering amplitudes. But these different time orderings are not just different bases or tricks. They actually lead to new formulas and new predictions. So we'll start with presenting 2 arguments. The first one is what we're going to use to anticipate crossing symmetry. And the second one is a discontinuity formula. So let me start.
Yeah, so it's the like the field emitted from scattering and the all time order correlated. Can it both be received just from the R ordering like you introduced?
Yeah.
So
Yes.
there's only one definition for R ordering, but it can magically. Oh, they form a basis, so you have to do some.
They form a basis, so it will be a sum of different R products. So you can use either T products or R products, but they're both bases, both perfectly equivalent. But something that might look simple in one basis might be like some long linear combination in another basis. But you can always use either or for any observable, basically.
Wait, so you just need to use one type of the ordering to form a complete basis.
Exactly.
Oh.
Exactly.
So what are the different basis factors in the set? Is it like having different amount of field in your time ordering, or?
Yes, you would need to basically sum. So let's see. Here we.
If I want to get out of time order correlator and a electric field from a scattered background, they are 2 different things. And what exactly should I do differently in the calculation to get these 2 different things?
Yeah, so as I say, in general, you'll need basically sums of different. You'll have to basically stick in the different time orderings or R orderings in different places.
Okay.
And then you'll have to sum over some linear combinations of those. But we have a section about that in the paper, how exactly to unfold one in terms of the other.
Okay. Thanks.
But yeah, the important point for now is that, yeah, you can pick one, basically, and use whichever one you want. Okay, so I wanted to include a few slides on anticipating the analytic continuations that we're going to talk about very soon in part 4. So in proofs of analyticity properties of scattering amplitudes from the 1960s, the retarded products are actually the star of the show. And there is a very good reason for that. The reason for that is because we basically impose that one particle is in the future of another one. So that's a theta function in position space. And after Fourier transforming, this buys us analyticity in momentum space because they're dual to each other. So basically, one thing that we can do here is that we can evaluate the retarded product, where 3 is in the future of 2. We can evaluate it in different momentum channels. So one momentum channel is when the energy of 3 is positive, and another momentum channel is when the energy of 2 is positive. So here it means that 3 is outgoing, and here it means that 2 is outgoing. But remember that the retarded product always puts 3 in the future of 2. So that's why basically we get this future operator for 3 and then the future creation operator for 3. So what this means is that one of these expressions is the scattering amplitude for 1, 2 going to 3, 4, while the other one, if you unfold it in terms of the S's and S staggers from before, is the conjugated scattering amplitude in this different channel. And this is precisely what crossing symmetry gives us, as we'll see in part 4. It basically relates the scattering amplitude in one channel to the conjugated scattering amplitude in another channel. So what we're going to see is that we can actually use this generalization, but we can string any set of creation annihilation operators in between here. So let me emphasize this. By allowing A and D to be strings of operators, we can relate scattering amplitudes and a different function. So here I'm going to put the A to be a 1 particle operator, A1 dagger, and D to be actually 2 particles, 4 and 5. So what the retarded product then relates, if we follow the same logic as in the proof of crossing from the 60s, is that it relates a scattering amplitude to a waveform. So we have not yet talked about any analytic continuations or anything. Let me remind you that this X is again a complete set of states. But I wanted to just emphasize this point because this is precisely what we're going to see in the last part, that these two are precisely going to be related by analytic continuations. So we'll revisit this point very soon. So what I want you to take away is that basically there is a connection by evaluating the retarded product between these two observables. And now we can start writing. So this is basically the second part of why it might be useful to use different bases. So for example, for this cut in the 4, 5 channel of this diagram, 1, 2 going to 3, 4, 5, we can rewrite it using these tricks as retarded products. But then we have a restriction because we know that 5 needs to be in the future of 4 and 3 needs to be in the future of 2. So we can consider the joint translation of 3 and 4. And remember, 4 is in the past of something and 3 is in the future of something. So we can actually never reach infinity if we take both and 3 and 4 together to infinity. So what this implies is that the discontinuity in the 3, 4 channel of this cut diagram is 0. So this might be a bit technical, but again, what I want you to take away is that it might be useful to use these different bases. Some things that are explicit in one basis might be hidden in a different one. Because if we use the time order products, we'd have to write this as some complicated sum, and it would not at all be clear that this joint translation of 3 and 4 actually cannot reach infinity, but using the retarded products, it's entirely manifest. Okay, so now that we've talked about L and C, I wanted to briefly talk about the physical properties of asymptotic observables before we go again to crossing, which is, to me, one of the most exciting parts of this story. So let me keep talking about the scattering waveform, as we could potentially measure in gravitational wave experiments. We've talked about how it's obtained from an in expectation value. And now with LSE, we have a new way of understanding this as an observable on a folded time contour. So basically time flows forward over here and then backward over here. So we're really measuring this graviton in the far future. And we can go ahead and compute this, and this was done around a year ago in these papers from 2023 by multiple groups. And we can actually compute this in the classical limit. So using, again, the techniques of Kosovo-Ramaybe and O'Connell, we can basically expand the propagators and the delta functions in large masses and add up these amplitudes and cuts. But as promised, we don't actually need to expand term by term. we can just directly work on the folded time contour and impose boundary conditions to fix which classical observables we're computing. So this becomes particularly simple if we're computing this using differential equations, because then what happens is that really the different time contours, so the different basically strings of s's and daggers, as daggers, simply enter in the very last step where we impose the boundary conditions. But these different boundary conditions actually have very drastic consequences, as promised before. So the inclusive observable has different analytic properties than the amplitude. So let's talk again about a scattering of, let's say, a black hole 1 and 1 prime to 2, 2 prime, and a graviton. So here we have a space-time picture of how this could look like. So we have some very heavy black hole here, 2, and then 1 that scatters off of it. And sometime along the way, a graviton is emitted. And if we compute this in perturbation theory, we would use Feynman propagators. However, if we instead compute this observable here, where the graviton is the only particle in the future, and we work on this folded time contour, then the propagators become retarded as required by causality. And in the one loop, we can literally work this out. And the infrared divergences are also different. And this we can actually work out classically as well, because for observables on a folded time contour, for basically these innen observables, there is a modified infrared divergence because we now have 2 sources of Shapiro time delays. So there's one delay from the graviton escaping the classical gravitational field. So this is one that's present both for the scattering amplitude and for the innen observable, or the waveform. So this is what's marked in red here. So this is basically just because if we have a gravitational potential, then the graviton gets redshifted and delayed because it has to escape that potential. So that's this delta T obs in this figure is supposed to represent that. But for the waveform, we have an additional term that's a time delay or a time advance from the 2 black holes approaching each other earlier or later than anticipated from classical motion. So let me try to explain this a little bit. So what happens here is that we have the black holes here, 1 and 2. And since this is an innen observable, we're basically implicitly fixing the distance between them. So if they were moving non-relativistically, it's maybe clear that they would start approaching each other and actually scatter earlier than expected due to their attractive force between each other. And this amount of earlier than expected is actually logarithmic in this initial separation distance between them. So that's this effect number 2, and it's actually not present for scattering amplitudes, it's only present for the waveform, or the innen observable. And this causes an extra infrared divergence if we assume that we start at infinity, that if we take r into infinity, we'll get an extra logarithmic divergence. And we can compute this both classically or using the Causal-Ramaybe-O'Connell formalism in quantum field theory. And I'm actually not going to go through it in detail. Let me just skip these details here for the sake of time. But the important thing is that we can compute it classically or in quantum field theory, and we get the same answer in both cases. And this has been verified by the groups that I referenced earlier.
Can I ask a question?
Yeah, of course.
So maybe this is a little, I think maybe a little off of what you're saying, so maybe we can defer it to later, but I'll just ask it anyway.
Absolutely.
So one of the things just conceptually, at least I find a little mysterious about this KMOC formalism is how I should is the question of how I should be thinking about infrared divergences, right? So my understanding is that you're able to get good results by just literally having a two-particle initial state, right?
Mhm.
But I might have thought that you need to somehow include an arbitrary number of soft gravitons in the
Mhm.
initial state, at least at some order. You see what I mean? You know, you need.
I see what you mean. Yeah.
Yeah,
Excellent.
you know what I'm talking about. So
Mhm.
do you have any comments on that, or do you want to just, maybe you want to just finish your talk and we can talk
Yeah,
about?
I have lots of comments on that, and I'm very happy to explain it. But yeah, maybe we should defer it till afterwards. But let me
Okay.
just say that this slide is actually the key to it, because we do expect an infrared divergence because there is classically a divergence in this case.
Yeah.
Because if we compute the time delay, it is divergent, and what a cloud of soft photons is going to do for you is that it's going to precisely say that the scattering actually didn't start at infinity at all. It's kind of going to push the answer back to some finite time at which we started the scattering. So the physically correct answer in this case, when we take Rn to infinity, is that there should be a logarithmic divergence in Rn. And the KMOC formalism precisely reproduces that divergence. So that's actually part of what we showed in this paper, is precisely that we had a prediction for what the infrared divergence should be for the waveform based on entirely classical computations. And then that's now been verified by the different groups computing it. So it's actually, yeah, it's a very mild infrared divergence in this case because it simply shifts this scattering time. And there's just a statement that if you don't know the initial separation between your two black holes, you will always have an ambiguity in the phase. But yeah, we can talk more about that later. Anyway, that's an excellent question. So yeah, let me maybe in the last 10 minutes or so tell you about new versions of crossing symmetry that we've already kind of hinted at. Let me start with a review on what crossing symmetry is. So crossing symmetry tells us that scattering amplitudes for two processes, AB going to CD, and a different process where I've switched some incoming and outgoing particles. So I take A C bar to B bar D, where this is supposed to be the antiparticle of C. Basically, that these two amplitudes are boundary values of the same analytic function, so that there exists an analytic continuation between these two amplitudes. And the argument used to justify this is that particles should be indistinguishable from antiparticles traveling back in time. But maybe you can anticipate from my question mark that we'll actually have to revisit this a little bit. And before we go on, let me also emphasize that crossing symmetry is not relabeling symmetry or cyclic invariance, and it's not CPT. So we can ask separately if the amplitude is relabeling invariant, for example, if we're scattering identical particles, or cyclically invariant. And CPT would be exchanging all of the incoming particles with all of the outgoing particles. So here we're exchanging a subset of them, maybe two at a time, or if we view these as some sets of particles, we might be exchanging a set of particles from incoming to outgoing. And what's nice about crossing symmetry is that it would allow us to use results from previous computations. So for example, if we have a process E plus E minus to gamma gamma, and we cross the positron and the photon, and let's say we've computed this left process to 10 loops or something, then as we get to the right process, we might not want to go through all of these computations again. And crossing symmetries would tell us that we don't need to. We simply use an analytic continuation to use our 10-loop answer for this process to get the answer for this one almost for free. But let me emphasize how entirely non-trivial this is, because crossing symmetry tells us that if we want to know how an apple falls to Earth, then we can equivalently compute the scattering process for Earth anti-Earth to apple anti-apple and do an analytic continuation to know what happens as an apple falls to Earth. Because an apple falling to Earth is a scattering experiment between the Earth and the apple. So this is why it's an entirely crazy idea from the outset that two things should be that there should exist an analytic continuation in the complex plane, because of course everything we do is with real momenta and real energies. But anyway, it turns out that it's actually true in 2-to-2 scattering. So crossing symmetry was proven for the non-perturbative amplitude at fixed momentum transfer t less than 0 in theories with a mass cap in these papers by Bros, Epstein, and Glasser in 1964 and 1965. And what happens is that we have a process up here. This is in the S complex plane, and I've taken S to be the Mandelstam invariant for the sum of these two momenta, the red and blue, on this diagram here on the right. And this is the S-channel physical region. And what they showed was that there is basically a bounded region here where we could possibly have singularities. So there are possibly some anomalous thresholds, or in other words, singularities in this shaded region here. But very crucially, this region is bounded. So there exists an analytic continuation in the unshaded region that can take us here from the amplitude to the conjugated amplitude in a different channel. So this would be the U-channel physical region approach from the opposite side. And since we can get from an amplitude to a conjugated amplitude, we can now do one more move to get back to the amplitude itself, and then we can establish crossing symmetry in this case. So if you had asked me, I guess a year and a half ago now, what happens for the 5-point amplitude, I would have thought that the same thing happened, that if we add an extra particle to this process, so we do E minus gamma to E minus E plus, and we cross here the positron and the photon again, then we would just get back the conjugated scattering amplitude for E minus to E minus gamma. But you might have guessed from all the question marks in these slides that the answer is actually that this is not the case. This is not what happens for the 5-point amplitude. And we've already kind of hinted at this earlier in the talk. If you remember when we were talking about the LSE formulas, that the R products hinted that the functions that were connected is actually not an S matrix and a conjugated S matrix, but rather these two observables here. So actually an S matrix and a waveform in this case. Because what the R product does for us is that it basically takes these A2 dagger B3 to a B3 dagger A2, keeping the other sets fixed. So this is the central result, that the result of analytically continuing scattering amplitudes are other asymptotic observables. And we learned in part 2 of the talk that analyticity arguments tell us that the retarded product, that we can use the retarded product to interchange basically these operators here. So we're not interchanging an S matrix and a conjugated X matrix, but rather just these two operators at a time. So now we've learned what actually happens if we analytically continue a scattering amplitude. What actually happens is that in the new channel, we land on this waveform, the expectation value of measuring a particle in the background of scattering of the other ones. So for example, if we wanted this expectation value of the electromagnetic field in the background of electron scattering, we could start with the S matrix for electron-photon going to electron-electron-positron and analytically continue in this complex Z plane. Maybe actually let me skip exactly what this Z is, but rather just tell you that it's a well-defined transformation that basically exchanges incoming and outgoing states. So that's how you can think about Z. And very crucially, it's an on-shell contour of analytic continuation. So we never take any particles on shell. So this gives us the crossing equation for two particle scattering. Basically, if we have any sets of particles A and one particle B scattering to a particle C or 3, and then a set of particles D, and we cross particles 2 and 3, then we get this generalized observable basically attaching these S blobs to the sets A and D. And you can see how at 4 points this reduces to what we had before. The minus sign is basically just from this I here. I would not worry about it too much. The crucial part is that an amplitude goes to a conjugated amplitude, and there is an extra I in the definition of S. But anyway, this at 4 points, what happens is because of stability. Actually, if this is just one particle, then nothing can happen in this blob here, this S blob here. So this is really a generalization of the 4-point result.
Right.
And
That's the question.
yeah.
Maybe. I guess maybe one of the reasons this seems so surprising is that, I mean, as you know very well, I'm sure that at the Feynman rules, naively crossing is quote unquote manifest, right? In other words, I write down some 8-loop diagram, and then there's a corresponding 8-loop diagram and a cross thing, and they're just gotten by exchanging the momenta and whatever. Okay.
Yeah.
Okay. But of course that doesn't prove it, because you have to actually do the integral, and you have to worry about all the singularities, and that's why it's difficult. But here's my question. So are you just saying that it's just wrong? I mean, that for any 5-point function or higher, crossing does not say what you think it says, and nobody ever checked a loop diagram and found this? I'm just confused about. You see, I'm just confused about this. This is just because you seem to be saying it's just the conventional statement of crossing is even wrong somehow.
Yeah. So let me first make the comment that I think it's extremely hard to prove in a generality that it's wrong, because what crossing wants to say is that there exists an analytic continuation. So one would have to prove that there, even by doing some crazy contour in the complex plane, you're never going to land on the amplitude.
Okay.
What we
so
can
that's not,
say,
you're not claiming that. You're not claiming that that's not true. You're just claiming this other thing is true, and you can see that in a much easier way than. Okay.
Yeah, what we're claiming is that if we follow the proofs for 2-to-2 scattering, sorry, the proof of crossing for 2-to-2 scattering, then this is what happens. And this actually brings me to a great point, which is that we're currently in the process of trying to prove this rigorously, because the proofs for technical reasons are, if you read through these proofs, they're hundreds of pages, they're extremely technical, and they're hard to generalize. However, our approach was simply to check what happens, precisely as you said, just do some loop level examples. So we have a proof at tree level, and at tree level, it's a matter of keeping track of kind of the delta functions of the propagators, because of course everything at tree level can be analytically continued to each other because we just have poles. But yeah, as I say, we're currently in the process of trying to get away from this point here of assuming analyticity. So we can have a proof in axiomatic quantum field theory, but we have to assume that the analytic continuation exists, and proving that it exists is extremely hard. And that brings me to this slide, that is actually not just something that needs to be ironed out, it's actually very, very subtle. So we do have some special cases where this analyticity can be very subtle, and we might need to continue past the anomalous thresholds. And we can understand this from axiomatic field theory, basically analyzing the anomalous thresholds of these diagrams. But it was very interesting to us that crossing is not something that we get for free. It's actually, it has a lot of subtleties. And in this case, what axiomatic field theory tells us to do is that we have to basically do an analytic continuation at very high energies to achieve what we want. And basically there is an anomalous threshold here that we have to continue past using this red path of analytic continuation and not the blue path. So let me emphasize that this is something that we understand from axiomatic field theory, but it's very, very subtle. So what happens is that the crossing equations give us families of observables that can be continued into each other. So for example, at 6 points, we currently have 3 different families of observables that can be continued into each other. What it means is that let's say I start with this observable here, and I want to get to this observable here, I can just find a path through this diagram that would get me an analytic continuation that would achieve that. However, we do not yet know how or in which cases the three families are connected. So we explored this one path of analytic continuation, but there could be other ones that land us on something sensible. So what we did also is that we checked all d-dimensional massless basis integrals for an expansion around d equals 4. So basically, for any, this will hold for any massless one-loop integral. And the surprise about that was that really these proofs from the 60s rely on the mass gap, but here we just checked it. We were not sure at all whether it was going to go through, but everything went through just fine. And we also have a proof at any multiplicity at tree level, which again might sound trivial, but it was actually highly non-trivial because we were precisely keeping track of the combinatorics of what the I epsilons of all these propagators were. Now let me just flash a slide of how we did these checks using the differential equations. So basically we had this pentagon topology and we had to check whether the original integral after the analytic continuation was the same as the waveform, which as you might remember is the conjugated amplitude plus a cut term. And this amounts to basically checking that all these matrices add up according to this equation to give 0. Excuse me, and that actually turned out to be true. So now we have our third way of computing the waveform. Before we obtained it either as an amplitude plus a cut, or we obtained it using L as Z. But now we have a new method. We can analytically continue the 5-point amplitude. And this again hopefully drives home how entirely crazy these crossing symmetry equations are. Because what it tells us is that if we want to get this expectation value of the gravitational field as measured, let's say on Earth in a gravitational wave experiment, then we can compute the conjugated amplitude for a very energetic graviton scattering with a black hole, and out go black hole, and anti-black hole. So that's, again, entirely non-trivial, but in principle, it could be done in these cases. Whoops. So that brings me to my conclusions. Sorry for going a bit over time. What we talked about is that asymptotic observables are those that we can form with an asymptotic algebra, just to answer the question of the title of this talk. We've talked about how these are measurable and computable and have new and interesting analytic properties. And then we talked about reduction formulas and a new version of crossing symmetry, which tells us that the S matrix contains a host of asymptotic observables, which are related by analytic continuations between different channels. So we now have an answer to what happens again if we continue the S matrix at higher points. We get back these different asymptotic observables as we change some particles from incoming to outgoing. So thanks a lot for coming, and I'm happy to take more questions.
So I have some remarks. It's really what you are doing is really very closely related to my work, but there are some differences. And particularly, I never considered analytic properties of this the amplitudes. But otherwise, this LSZ formula, I believe, is more general in my setting. But what is probably more important, that you consider this asymptotic observables in the case when you have usual scattering matrix. But inclusive scattering matrix, that is my form of your asymptotic observables, can be defined even in the case when you do not have any normal scattering matrix.
I see.
For example, in electrodynamics, you don't have conventional scattering matrix, you have only inclusive scattering matrix. Another thing, I have a formalism that I call formalism of L functionals that I invented long ago. And this formalism, I believe, allows it is computationally much easier. So what did you consider? You considered these gravitons which are generated in collision of black holes. Assume that you definitely you disregarded the action of gravitons on black holes.
Yeah, exactly.
And so that in this situation, this formalism of L functionals allows to solve the equations of motion explicitly.
Fantastic.
But so I don't think that I should really explain my work.
Definitely, if you could send those papers to me, I would be thrilled. Yeah.
So I hope that I will send. There are several papers.
Fantastic.
But basically, probably last 5 years, all of my papers have some relation to inclusive to the stuff that you are doing.
Fantastic.
To inclusive, at least to inclusive scattering matrix. And also, now I'm finishing a book, a mini book for Springer. I hope that I will finish it tomorrow. I can say to you that the almost final draft, all the stuff is.
I would love to see it. Thank you so much. Yeah.
So I hope I will send this to you and to your collaborators.
Oh, that's fantastic. Thanks a lot.
Say hello to Sebastian.
Yeah, I will. I know you.
Okay.
Collaborated.
So thank you very much for interesting talk, and it's very pleasant for me that
Thanks for
people
coming.
Are doing now the stuff that I was interested in for for many years now.
Yeah,
and so
absolutely.
That's very nice. And by the way, he'll give a talk on 14th of June. Which will be has a name, inclusive scattering matrix. The title is inclusive scattering matrix.
Where is the talk?
This is the talk in Bir-Sherivet. This will be a conference. It will be a celebration of my 70 years in science.
Oh, wow. Amazing.
So that's, I hope that it will be, definitely it will be on YouTube, but probably
Fantastic.
it will be available in Zoom also.
Yeah, excellent. Thank you for letting me know. I appreciate it.
Okay. So thank you for nice talk.
Thanks, likewise.
Goodbye.
Goodbye. We have some more questions, comments?
So with like cross sections and scattering amplitudes and things like that, that's been, as far as I understand, all of the observables we've needed for our like particle experiments for however long we've been doing particle experiments. So what would these observables provide that we haven't yet been able to measure in our current like LHC style experiments?
Yeah, so I think part of our story was to basically put this in a unified framework rather than directly come up with new observables. Because I mean, for example, these observables, as I say, are something that have been measured and computed. And that was actually part of the surprise to us when we started, especially when we started looking into the story of crossing. That actually, once you do the analytic continuation, you land on something that is sensible. So that was more our approach, not to say that we have some new observables, but rather to connect with what people precisely have been computing before.
Okay,
if that makes sense.
I need to ask a more elementary question. I was just kind of confused about when you were talking about the observables where you have an S and an S dagger. And so that would imply that like all 4 of those electrons are in the past and the photon is the one thing in the future.
Exactly. So let me
And-
go back maybe.
This was
So there
something
was
that
a
I just
slide.
didn't follow. But
No problem.
kind of
Thanks for asking.
physical process is that when you have 4 electrons in your past and none in your future.
So it's actually, I had this somewhere here. So it's actually, because it's like a retarded product, it means that the graviton is the only one in the future.
Okay.
In this particular case. So time kind of goes alternately backward and forward, if that makes sense. So this is like an expectation value, where these are the particles that we measure in the future. And these are the particles in the past. Excuse me, the 1, 2, and 1 prime and 2 prime. And usually we think about an expectation value as something squared. But here it's actually not squared because we're measuring a field. And a field is linear, like whether it's the electric field or the gravitational field, it's linear in the creation annihilation operators. So that's why we get this diagrammatically, this one particle in the future, and then of course everything else that we sum and integrate over. But then it's sandwiched as an expectation value between the instates, basically. So this 1, 2, 1 prime, 2 prime are really the instates. So that's why it's an in and observable. We measure
Okay,
something
so-
in the future, fixing the initial states.
So should I interpret this as 4 or like 2 black holes, 2 anti-black holes annihilating and producing 1 graviton?
So it would be 2 black holes scattering off each other, emitting a graviton, or emitting whatever they emit, but we measure some signal of a graviton on Earth, some signal of gravitational waves. So yeah, it would basically be fixing that our initial states are 2 black holes that scatter off each other, and we have no idea what happens. Lots of things happen, lots of radiation goes out in all different directions, and that's what this X represents. But we know that we measured some displacements of our detectors on Earth. So that's what this H is.
Okay, so this is what we do if we have like incomplete information about the final state.
Exactly, exactly. So the way
Okay.
I think about it, as I say, is that in a particle detector, we try as hard as we can to measure all the outgoing particles with as close to a spherical detector as we can, maybe apart from the beamline itself. But it's kind of the polar opposite situation that we have in these gravitational wave experiments, because the scattering occurs somewhere out in the universe, and then we don't have a detector. We have no way of knowing like what happened basically on a sphere around the scattering experiment, right? We only have this kind of tiny corner of phase space of what we measure on Earth. So that's why we have to integrate over everything else that could have happened, and that's the natural observable to compute. Does that make sense?
Right. Yes, thank you.
Thanks, likewise.
Well, I think since we're about 15 minutes late, so what I think we should do is we should thank Hofie, and if she's willing to stick around, we can ask some more questions, but if people want to leave, they're excused.
Absolutely.
Okay? So let's thank Hofie again for a very nice talk.
Thanks for coming.
And like I said, anyone who wants to stick around, if Hofie, what's your situation? Are you able to stick around?
Yeah, I
for-
can